Hi, I'm Ben-Yaakov. This is a primer to active and switched capacitor filters. Filters are electronic circuits that exhibit a certain transfer function as a function of frequency. For example, a low-pass filter will be a filter that will transfer frequencies at low frequency. A high-pass, high frequency. Band-pass at a band of frequencies, and band reject will sort of reject some frequencies in this particular region. When expressed as a Laplace transform transfer function, a filter will normally include some numerator and denominator, which actually will determine the type of the filter. Now, here's a typical filter in which we can see that there are some characteristics that we are interested in. For example, we like to have certain degree of roll-off, that is how fast does it attenuate the frequencies above a given point, the ripple that it might have, and then some of the residual response beyond the frequency in which there is a cutoff. Here are some examples of second order filter responses. For example, a low pass second order will include two complex poles. A band pass will include two complex poles plus a zero at the zero origin. A notch or band reject will include two complex poles plus two zeros. Here is the transfer function. And then the high pass will include two complex poles, a zero, double zero actually at the origin, and an all pass. All pass means that it's sort of constant response, except that there is, of course, a shift of phase that in some application you might be interested in. In this case, we have a complex pole plus two real zeros. Now, here are some examples of the responses of sort of practical filters. There is the Bessel filter, the Butterworth, the Chebyshev filters, and you can see that these are for the low-pass response. And here is also the same filters, except that the roll-off here is different. That is for example, the Bessel function here goes very quickly down, while in here it's sort of moderately. Some cases you'd like it to go very quickly to cut off, but it will affect the phase and the time response. So in some application, you have to tailor the response to the particular application. A very interesting filter is the Butterworth filter. In this case, in order to get this response, we have to have the poles on a half circle on the left side of the complex plane. And in this particular case, we see here two complex poles, another two complex poles, and another real pole. Now, in the case of the Butterworth, these should be equally distributed in this half circle. This will be a fifth order filter because we have 1, 2, 3, 4, 5 poles, and the roll-off will be minus 20 dB per decade times 5. So it's going to be going down very fast. Now we can realize filters by passive network. This will be a passive filter. We'll have an inductor, a resistor, and a capacitor. We do have to have both an inductor and a capacitor in order to have a second order equation. Using a passive network, we can realize various transfer functions. For example, the low pass, the band pass. The difference between these two order transfer function is, of course, the numerator, which will determine whether it will be a low pass, high pass, or band reject. Now, what's the difference between active filters and passive filters? The difference is that an active filter is built around an operational amplifier, and the very important feature of it that it has no inductors. This is the main feature of active filters. Now, with the operation amplifier and some passive R and C elements, we can emulate a second order transfer function. This second order transfer function will be a basic building block, and by chaining a number of building blocks like this, we can realize various types of filters. That is, each one will be responsible for at most two poles and by adding these, we can get whatever filter we would like to build. Here is, for example, a template for such a network around an operation amplifier, and then it happens this will be the transfer function between V in and V out. This is a generic presentation, that is, it is just a function of these admittances, and this is the transfer function. And by choosing here, for example, a capacitor, here say a resistor, we can get various type of transfer functions. For example, if we put here a capacitor, resistor, another capacitor, we'll get this transfer function, and by this we can realize one building blocks, and by adding these building blocks we can get whatever filter we would like to realize. Another family of active filters is the active filters which are based on differential equation. And let me just illustrate it by this particular case. Suppose we would like to build a circuit that will emulate this transfer function. This is in the Laplace transform. It's a second order transfer function. And what we do, we like first of all sort of to express it as a function of V out, and we have the various elements here, which is just another way of expressing the relationship between the input and output. In this approach, we are using integrators. Integrators are really nice because they smooth out noise, so they are very good in terms of noise performance. And the basic integrator will have this transfer function. Now the values of the resistor and capacitor depend on the gain or the transfer function that we need, and also we have here a degree of freedom. We can sort of scale it in ohms, mega ohms, and microfarad, so that the product, which is shown here, will be the value that we actually would like to realize. So now we have this expression which sort of relates V out to these terms. Notice that in these terms we have one term here is a function of V in, here we have function of V out, and here is a function of V out. So what we are going to do here is actually to go from the end backward. So suppose this is V out at the output of this amplifier. Now we are going to realize these two terms. This is a first order, this is just an integrator, and this is just a double integrator. Okay, so here from V out we go back, and here we have this integrator. We need this inverter because we have an inversion here, so by putting this inverter we sort of take it into account. The minus is actually provided by this, the minus that we need here is provided by this integrator. And then we have the second term, which is a double integrator. So we go from here and we go through in one integrator, and there is another integrator. Now we have to add to it this expression here, which is a function of V in. So here we have V in coming through an integrator with some constant, which is this constant. And then we go through another integrator to get the double zero here. This amplifier is actually doing this summation of this term, and this term, and it goes into the amplifier and goes out. This is sort of a feedback circuit that keeps itself alive, and the driving force is, of course, the V in. Transfer function between V in and V out is the transfer function that we actually wanted to realize with this particular approach. Another way of building active filters is to use switch capacitors. Now the advantage of switch capacitors is that not only that they don't include an inductor, they don't include a resistor. They are built around an operation amplifier plus capacitors. And it turns out the transfer function are a function of ratios of capacitors, say C1 to C2. This is very good because in integrated circuit, it'll be very difficult to fabricate a very precise capacitor, but it is relatively easy to fabricate a ratio of capacitor, which will be very accurate, because the ratio is actually a function of the areas. So you can make the areas very accurate, so you can get very accurate areas. So this switch capacitor circuit behaves like an integrator, and this will be the transfer function, and this will be the basic building block of the active filter in the differential equation approach. Now what we have here is a capacitor plus a switch, which is sort of connecting the capacitor to the input and then to the virtual ground. Here is virtual ground, that is, the voltage here is zero due to the feedback through this path. We can calculate the equivalent resistor which represents this particular switching circuit. Remember that here we have virtual ground. Now the calculation is based on the fact that we are charging the capacitor here to the input and then dumping it into the virtual zero, or the input of the operational amplifier. Now the average current will be the charge over the period, or charge times the frequency. Charge is capacitance over times voltage, V in, which is coming from here. So the average current is this value, and the equivalent circuit is the voltage that we see here divided by the average current that is flowing here or flowing here. And as it turns out, our equivalent is 1 over C times the frequency. Plugging in the value of our equivalent into the transfer function 1 over SRC, we find that this is the transfer function of this particular integrator. Now, as I have said before, we see here the expression is a function of the ratio of two capacitors, which is very nice for integrated circuit implementation. Furthermore, it's also a function of the clock. So by changing the clock frequency, you can actually change the value of RC, and therefore you can actually build a filter which has a controllable cut-off frequency, for example. These active filters, the switched capacitor active filter, are actually built as an integrated circuit. You put the capacitor usually at the output, and you can then program it to emulate any given or a number of filters of low pass, band reject, or band pass. Of course, you can put this switch capacitor in the feedback, and then you'll get a sort of a low pass filter, simple one like this, because this is now this switched capacitor, and this is this switched capacitor. This brings me to the end of this presentation, which is short and just gives a feeling of what are active filters, what are they all about. I thank you very much for your attention. I hope you have found this presentation of interest, and perhaps it'll be useful to you in the future. Thank you.